Okay, so in terms of heuristics, that's all that we had. However, there are some tricks that always exist, and let's also use those tricks, which may appear to be extremely funny, but then practically the constraints and the constraints graphs that you get for realistic problem may actually have that. This time we will be exploiting what is called as the structure of the problem. So we'll try to see that if there's something that can be exploited as a structure, and it turns out the old constraint graph that we actually had a wonderful little thing which we did not observe so far. And the wonderful thing was the fact that f is completely disconnected to everything else. It's just disconnected. So I could solve this independently and this independently, and I could get a solution. Just merge the two solutions up. It doesn't matter what are the solutions. So nothing over here puts a constraint over here. Nothing over here puts a constraint over here. So instead of d raised to power n, I have d raised to power n minus 1 over here. And this is just d raised to power n, which is a d raised to power 1. Now, how do you divide a problem like that? That's a standard problem of finding subgraphs. So find out the subgraphs, depth first search, find out how many disconnected graphs exist, depth first search, and solve each of the problems separately. In general, now I'm not calculating the complexity as a worst case. If I have in my complete graph disconnected cycles, each one with a maximum length of c, then d raised to power c is the total computation that I have to do. Drawing it visually, so I say instead of this graph of n, I on close observation observe that these are cycles of maximum length c, and there will be n by c such cycle. So it's an exponential on the cycle length. However, c could be reasonably smaller than n. So how much is the maximum number of nodes that you have in one subgraph in the constraint graph? And because c could be substantially smaller, therefore anything in the exponential, as long as it's coming down, it's a very good sign. It's a curse of dimensionality. Now, of course, this example was made up, and it's of course unlikely that somebody would design the problem such that there are too many disconnected subgraphs. It doesn't practically happen. So there's another structure, and this is more interesting. So for the same subgraph, let us take something like this. Now, if you observe, this is not a constraint graph. It is a constraint tree. And of course, tree is a special case of a graph. So you look into the graph and you said that for n vertices, you observed that there were n minus 1 edges. And surprisingly, not only were there n minus 1 edges, you couldn't take out a subgraph. That means what? It's a tree. Wonderful news, you've got a tree. Now, In principle, whatever I said of course holds, and you could still use backtracking to solve it. However, there is a very easy way to make this tree strongly inconsistent. And strongly inconsistent means I will not have to backtrack. So there's an easy way to make the tree strongly inconsistent. So all that you do is that you arrange these things in a nice topological sorted order, and the topological sort can have different results. I'll take any one of them. Let me take the F first, and then let me take in a B, E, and a G. So now I need to make it somehow strongly inconsistent. What you do is go in the inverse order of the edges. First go on this edge, which is all the edges which are leading to the last node G. Then go on this edge, all leading nodes to the edge E. Then go on this edge, then go on this edge, then go on this edge, then go on this edge. And you make this edge consistent, 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 and you make this edge consistent. Each one of them making edge consistent is d square, and in all you have n nodes to visit. So that's how you can make in the graph as edge consistent with each one of them. Now it turns out if it's a tree, this is the output of being strongly inconsistent. It turns out this is the edge of being strongly inconsistent because in the topological order you are only deleting edges all the way up over here, which by the same principle means that no other edge will get inconsistent because I'm only deleting the nodes from a prior node, and because I'm doing that I make it strongly inconsistent. What that means is now you could go start filling up values without the need of backtracking. So you could arbitrarily take a value over here, take any value over here that is consistent with this, take any value over here that is consistent with this, take any value over here that is consistent with this, and so on and so forth. So we hate graphs, but we love trees. A complexity which was ideally d raised to power n now turns out to be nd square, or from exponential I've got into a polynomial complexity. There cannot be anything better. So as long as it's a tree, honestly in CSP we'll not care about it. The complexity is polynomial and we'll just absolutely love it. The complexity is polynomial, and nd square algorithm without backtracking will solve it. The complexity is polynomial. However, you may say that, again, this was a made-up problem. Practically, will we really have a tree instead of a graph? We understand that graph takes a lot of time. Tree on contrast takes absolutely no time. Will we ever get that? And the answer is obviously that's, again, a made-up problem. However, many times you can convert a graph to a tree by making a cut, and that's the cut that you make. So if you make this cut, the problem becomes C, A, B, E, and a D. This is just a node, but let's call it as a graph, and this is a tree. And these are two separate problems. In general, this is called as a cut set, a set which is just one here of vertices which are taken out of your constraint graph, and after taking out, the resultant graph is just a tree. And we love trees. It has polynomial complexity. So it appears to be a very nice problem, but unlike previously, we have not decomposed it up into two independent problems. These problems are related because, of course, they are connections which are invisible. Actually, they exist. So now what my algorithm is really gonna be, I've got a cut set which is of size C, and I've got a tree which is of size n minus c, and this is a very simple and easy problem, and this is a difficult problem. So at any point of time, if I am to solve this one, I'll say naively solvable. If I am to solve this one, I'll say that, okay, something really needs to be done on this. So let's do a simple little thing. Let us solve this problem, which is of the cut set, get a solution. Using that solution, now we've got values to all the variables over here, which means that these are assigned, which means that I can delete in corresponding values from the domain. So suppose the solution over here was d is equal to r. I can go about deleting r from each one of these domains, and now guess what? It's actually a tree. I just need to solve it up. You get the solution fine. Otherwise, instead of saying not possible, you get a second solution. You plug it around into here and very easily you solve that. This is the hardest step. So now what really happens out in terms of the complexity is, in the worst case, I'll have to solve this entire problem consisting of n nodes and get all the solutions. The last solution will give me a solution in the tree. So the general complexity is d raised to power n. In this case, the number of nodes are c, so it's d raised to power c. This is getting all solutions for Cutset graph. And once you get the solution, you plug in over here. And once you plug that in over here, what is the complexity to solve this one? There are n minus c nodes. So out of n, c got here, there are n minus c nodes, and it's n minus c d square. That's what the complexity turns out to be. I'll write it down over here that the number of nodes are c over here, and the number of nodes are therefore n minus c over here. And that's absolutely interesting, because while you may not get graphs, but you may get in graphs from which, with a small cut set, say 5, 6, 7 nodes, you get a tree. And once you get a tree, you know it's very easy to solve. There's a little caveat here also. So I did not tell you anything about the algorithm that cuts some nodes from a graph and makes them a tree such that the size of the graph is minimized. So my cut set out of all the infinite possibilities is the one that has the least number of nodes, and the non-cut set part of it is still a tree. That's the quality of a cut set. So I append that over here, cut set that divides graph to graph of minimum size plus a tree of maximum size. Now, I'll tell you about the algorithm that does that, and it is a difficult algorithm. And if you go upon formally solving this problem, this algorithm will take in most of the time. However, there are approximate solutions which are possible, and again, heuristics could be used in order to approximately get something that divides a graph into graph of smallest size and a tree of the large size. Now, per se, the local algorithms are not into the course, and that's why in every chapter I'll not be dealing with the local algorithms. There's a separate course that does that. In this one, I am a little bit tempted to give you a local algorithm. So the way we make the timetable for you people is not this backtracking. The person in charge will bang his head. God knows what will happen. So it goes upon start with a random solution which will mostly be not constraint free, and then you repeatedly try removing constraints till solution is constraint free. Now, I'll not go into infringing the other course, why global, why local, pros, cons. Now, the heuristics is applied over here. So I've got a constraint solution. How do I remove the constraints iteratively so that constraints reduce? That's actually what happens. So first timetable is floated, then people say this is a constraint, that's a constraint, the committee sits in, tries to locally mend that up. So this thing over here is basically nothing but find one variable which is violating constraint. That's what the committee does, and give it a better new value. So I'll say, hey committee, my AI course is at the same time as my other course on robotics, so I cannot be at the same place at the two times. So timetable committee will look at the AI course which is causing the constraint and will try to give it a new value. Actually, robotics one will be a lot more easier to move, which is why many times there's a problem with the timetable. I don't go to the committee, I tell the committee such small constraints, even I'll remove it. Now, you always give it a value around over here which has the least constraints, also called as the minimum conflicts. So out of all the values, you try the value which has the minimum number of conflicts. So that's what's a very good heuristic. And the reason is that structure, graph, backtracking, whatever, we mostly do have constraint satisfaction problem which are under constraint. There are too many variables, but then there are not many constraints. So even a random solution adheres to many of the constraints, and then you go upon picking variables, trying new values which are minimum conflicts. The majority of the constraints get easily satisfied and you get a solution. Sometimes, unfortunately, what happens is that while you're doing this, you observe that there are 15 constraints which, no matter what, are not getting solved. So now you reverse your strategy. It's called as giving importance to constraint. Now you get a solution which at least adheres to those constraints, and while it adheres to those constraints, the others may be constraint free, and then you do this minimum conflict such that you don't violate the constraints, which are those tedious constraints which are not letting anything happen. So in this university, you could find out what those constraints are, who is putting those constraints, which are very difficult, and therefore all we do is we first satisfy those constraints. Rest we'll be able to work out ourselves. This unfortunately also has an element of learning, as you might call it, in a not in a very obvious sense, that how do I identify which is that terrible constraint which is violating. And why am I telling you that? Because initially I started off with CSPs are so popular that so many variables it can easily solve. It turns out approaches like this are often used along with things like backtracking, and they are the ones who really accelerate those things. Unfortunately, local algorithm is not in this course, it's at some other course, which is the power behind a lot of CSPs getting easily solved. So that'll be all for the lecture. Thank you.